We are now starting with the chapter 3, actually and particularly very useful and important metric spaces are obtained on a linear space by introducing a suitable norm and induce a metric. So, we shall discuss on a particular type of metric spaces called norm linear spaces. Whenever this norm linear spaces is complete with respect to a metric induced by a norm, we say it is a Banach space. So, the study of linear operators, bounded linear operators on such spaces, that is norm linear spaces, Banach spaces, are highly developed part in functional analysis. The chapter 3 is divided into 4 modules. Module 1 consists of some preliminary ideas on linear spaces, what we have learned in undergraduate courses. So, in this module we now recall the preliminaries of linear spaces. In module 2 we shall have a overview on a norm linear space, and thereby we shall put an idea on convergence of a sequence in a norm linear space. In module 3 we shall explain on some examples on Banach spaces. In module 4 we shall discuss on completeness property of a norm linear space, and thereby we shall explain on characterization of completeness of a norm linear space. Now, we shall discuss on chapter 3. The title of this chapter 3 is norm linear spaces and Banach spaces. Among the 4 modules, we shall start with module number 1, that consists of some preliminary ideas on linear spaces. So, we now recall a definition of linear spaces. Let R or C denote the field of reals or complex numbers that are also called scalars. A linear space, sometimes we say it is a vector space denoted by generally V, is a collection of objects or elements called vectors satisfying V is additively an abelian group, that is V is commutative group with respect to addition. The identity element is the 0 vector, rather we say it is a null vector of V denoted by theta or 0 vector. For every pair alpha comma V, alpha being a scalar and V is an element of V, that is V belongs to V, there is a vector denoted by alpha into V, not V alpha, called a scalar multiple of V, such that the following properties holds. Number 1, 1 into V is equal to V for all elements V belonging to V. Number 2, alpha into U plus V is equal to alpha into U plus alpha into V for all scalars alpha and for all vectors U comma V belonging to V. Number 3, alpha plus beta dot V is equal to alpha dot V plus beta dot V for all scalars alpha and beta and for all vectors V belonging to V. Number 4, alpha dot beta dot V is equal to alpha beta dot V for all scalars alpha and beta and for all vectors V belonging to V. We generally denote alpha dot V by alpha V. Examples, we know that in undergraduate courses that real number space R or space of all complex numbers is a vector space with respect to usual addition and scalar multiplication of a vector. We shall start with another example, is that let Rn be the collection of all n tuples of reals like x is equal to x1, x2 dot 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 xn, where the elements xi are taken from space of all reals R. Thus, Rn becomes a linear space with respect to real scalar field where addition of vectors and scalar multiplication of vector are defined as the following, that is x plus y is equal to x1 x2 dot 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 xn plus y1 y2 dot 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 yn, where y is taken as y1 y2 dot 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 yn. So, x plus y is equal to sum is taken as coordinate wise, that is x1 plus y1 comma x2 plus y2 dot 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 xn plus yn, which is an element of Rn, and alpha into x is equal to alpha x1 x2 dot 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 xn is equal to alpha xn comma alpha x2 dot 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 alpha xn belonging to Rn, where x belonging to Rn and x is taken as x is equal to x1 x2 dot 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 xn and alpha be any real scalar. Here Rn is also Euclidean n space with 0 vector is equal to 0 0 0 dot dot up to n, that is all coordinates are 0, and it is called a real vector space or real linear space. Now, we shall encounter with another example of a vector space. Let Cn be the collection of all n tuples of complex scalars like z is equal to z1 z2 dot 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 zn, where zi belongs to C. The symbol z is used because z is an element of complex numbers. Thus, Cn becomes a linear space with complex scalar field where addition of vectors and scalar multiplication of vectors are defined as z plus z dash is equal to z1 comma z2 comma dot 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 comma zn plus z1 dash comma z2 dash comma dot 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 comma zn dash is equal to coordinate wise sum, that is z1 plus z1 dash comma z2 plus z2 dash comma dot 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 comma zn plus zn dash, where z dash is equal to z1 dash comma z2 dash comma dot 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 zn dash belonging to Cn, and alpha z is equal to alpha z1 z2 dot dot zn is equal to alpha z1 comma alpha z2 comma dot 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 alpha zn, and alpha be any complex scalar. Here Cn is also called Euclidean n space over the field of complex numbers with the 0 vector. 0 vector is equal to 0 0 0 0, all the coordinates are 0, where 0 is equal to 0 plus I into 0. So, we shall explain another example of a vector space. Let CAB denote the collection of all real valued continuous functions over a closed interval a comma b. Then CAB is a real linear space corresponding scalar field being that of reals, where vector sum and scalar multiplication are defined as follows, that is a plus g t is equal to f t plus g t, a less or equals to t less or equals to b, and f and g are taken from CAB, and alpha f t is equal to alpha f t, where a is less or equals to t less or equals to b, and alpha be any real scalar, and f is taken from CAB. Since we know that the sum of two continuous function is again a continuous function, so is a scalar multiplication of continuous function, we see that a plus g comma alpha f belonging to CAB, where f comma g belongs to CAB and alpha being any scalar. Here the 0 vector of CAB is the 0 function denoted by capital theta, that is theta t is equal to 0 for all t belongs to AB. So, there are another examples like the sequence spaces LP 1 less or equals to p less or equals to infinity, space of all bounded sequences L infinity, space of all convergent sequences C. That means if we take an element x belongs to a C, that is x is equal to xi1 xi2 dot 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 xi(n), where xi(n) converges to an element, then we say this is an element of C. Space C0 of all convergence sequences converging to 0. Space of all polynomials PAB, that is space of all polynomials curly PAB, and space of all square integrable functions capital L to AB, etc. These are the examples of linear spaces, rather examples of linear spaces in infinite dimensional spaces. Up to this, in this module 1 of this chapter 3, we have been acquainted with the concept of linear spaces with the various examples both in finite dimensional cases as well as in infinite dimensional spaces. Now, we shall concentrate upon the subspaces of a linear spaces. Now, we are going to discuss in detail. Now, we shall discuss on algebraic operations of subsets on a linear space. The definitions looks like this: if capital A and capital B are subsets of a linear space V, then A plus B is the collection of all such elements A plus B, where A runs in A and B runs in B. For any scalar lambda, lambda A is the collection of all such elements lambda A, where A is taken from capital A. The subset A minus B means the collection of all such elements A minus B, where A belonging to A and B belongs to B, and A minus B is equal to A plus minus 1 into B. Here minus 1 can be considered as a scalar, and for scalar lambda is equal to 0, 0 into A is equal to 0 vector. Also A plus B is equal to B plus A, because vector addition is commutative. It is to be noted that A minus B not equal to B minus A, that is the set A minus B is not equal to the set B minus A. Do not make any confuse that A minus B is equal to A intersection B complement in set theory approach. So, now we explain how result comes A minus B is not equal to B minus A. In fact, if we take A is equal to the singleton set 1, 0 and B is equal to singleton set 0, 0 in R2, that is the Euclidean 2 space, we find A minus B is equal to singleton set 1, 0 and B minus A is equal to singleton set minus 1, 0, and that is why A minus B is not equal to B minus A. It is also to be noted that A plus A is not equal to twice A. In fact, if we take capital A is equal to the set consisting of all elements 1, 0 and 0, 1, which is a subset of R2, then A plus A is equal to 2, 0, 0, 2, 1, 1, that is the collection of all such elements 2, 0, 0, 2 and 1, 1, and 2A is equal to collection of elements like 2, 0 and 0, 2. Given a fixed member B belongs to V, we note that B plus A is equal to collection of all such elements B plus A, where A runs in A is called a translate of a set capital A. Let capital X denote a linear space over the field of reals or over the field of complex scalars. Given x1 x2 dot 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 xn belonging to capital X, and for a given set of scalars alpha 1 alpha 2 dot 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 alpha n, the vector sigma I equal to 1 to n alpha I xi of capital X is called a linear combination of x1 x2 dot dot xn. Alpha I xi belonging to capital X. A subset C1 of capital X is said to be span or generate X if and only if every member of X is a linear combination of some vectors of C1. That means X is spanned or X is generated by C1. Elements x1, x2 xn of capital X is said to be linearly dependent in X if and only if there are corresponding member of scalars alpha 1, alpha 2 alpha n not all 0 simultaneously, such that sigma I equal to 1 to n alpha I x I is equal to 0 vector. A finite number of elements x1, x2 xn of capital X are said to be linearly independent if they are not linearly dependent. That is to say, sigma I equal to 1 to n alpha I x y equal to 0 implies alpha 1, alpha 2 alpha n all are equal to 0 simultaneously. An arbitrary system of elements of capital X is said to be linearly independent if every finite subset of the given system becomes linearly independent. Note that if a set of vectors in capital X contains a linearly dependent subset, then whole system becomes linearly dependent. But a linearly independent set of vectors does not contain the 0 vector or null vector. A non-empty subset capital E of a linear space X is called a subspace of X if sum of two elements belonging to E where the elements are taken from E. That is, if X and Y are both in E, then X plus Y belonging to E, and also alpha X belongs to E whenever X is in E and alpha is any scalar. Now, we shall show, rather we shall explain on another example, that is, let E be a non-empty subset of X if capital L is the set of all linear combinations of elements of E, then L is a subspace of X. It is a routine verification that L is a subspace of X. This space L is called the subspace spanned or generated by some elements which are taken from S. Note that the subset, the singleton set 0 vector, is a subspace and is known as the null space. Now, in this regard, we shall explain on a theorem. The theorem looks like this, that let x1, x2 xn be a set of n number of vectors with xi not equal to 0. Then the set x1, x2 xn is linearly dependent if and only if one of the vectors x2, x3 xn, say xk is in the subspace generated by the remaining vectors x1, x2 xk minus 1. The proof is like this. Suppose the given set of vectors is linearly dependent, then there is a smallest k with 2 is less or equals to k less or equals to n, such that x1, x2 xn is linearly dependent, and we have alpha 1 x1 plus alpha 2 x2 plus plus alpha k x equal to 0 with not all alpha i's are 0 scalars. Obviously, alpha k not equal to 0, otherwise x1, x2 xk would form a linearly dependent set. Consequently, xk is equal to minus alpha 1 by alpha k into x1 minus alpha 2 by alpha k into x2 minus minus alpha k minus 1 divided by alpha k into xk minus 1. That is, xk is in the subspace generated by x1, x2 xk minus 1. Conversely, if one can assume that some xk is in the subspace generated by x1, x2 xk minus 1, then we have xk is equal to beta 1 x1 plus beta 2 x2 plus dot 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 plus beta k minus 1 xk minus 1. That is x1 x2 dot 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 xk are linearly dependent, which in turn we have the set x1 x2 dot 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 xk is linearly dependent. Now we shall put another definition. If in a linear space capital X there is a positive integer n such that X contains a set of n vectors that are linearly independent, while every set of n plus 1 vectors in capital X is linearly dependent, then X is called a finite dimensional space and n is called the dimension of X, and we generally write dimension of X is equal to n. The null space is finite dimensional of dimension 0. If X is not finite dimensional, it is called infinite dimensional. Now, in case of the real numbers, the dimension of R is equal to 1. The dimension of C over the field of complex numbers is equal to 1. The dimension of C over the field of reals is equal to 2, and the dimension of CAB, LP, L infinity are all of infinite dimensional. Now we again put a definition that a finite set capital B in a linear space X is called a basis of X if B is linearly independent and if the subspace generated by B is all of X, that is, if the subspace spanned by B is whole of X. It is to be noted that if x1, x2, xn is a basis for X, then every member X belonging to capital X can be expressed as X is equal to I equal to 1 to n alpha I xi as a sum where scalars alpha i's are uniquely determined and the representation of X in terms of basis members is unique. Let dimension of X is equal to n where n is greater or equals to 1, then X has a basis consisting of n members, that is, n members of X are linearly independent, which generates the capital X. For X certainly contains vector x1 x2 dot dot xn that form a linearly independent set. Now for any member X belonging to X, the set of vectors x1 x2 dot 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 xn including the vector x consisting of n plus 1 vectors must be linearly dependent. So we conclude that X is in the subspace generated by x1 x2 dot dot xn by earlier result, hence x1 x2 xn form a basis of X. Now we have come to an end with the concept of a vector space and subspaces. In this module 1 of chapter 3, we have learned the basic results on vector spaces and subspaces and related to their dimensions. Now we are going to the module 2 of chapter 3, what we call as a basic properties of nonlinear spaces.